Hello everyone. In the previous lecture we have learned about dynamic logics and the problems associated with it. In this lecture we'll be trying to solve trying to go into the other circuit family members to see if those problems can be solved. So the next member of the circuit family is Domino Gates. What it does is it connects a dynamic gate with a static gate. So dynamic and static pair is created, and it creates domino logic. Now in the after every dynamic stage we have an inverter which is a static stage. So here we have an example of dynamic NAND gate in this case, and after that we are connecting an inverter, static inverter. So this whole part makes dynamic or domino AND gate. Why is it domino? It is domino because uh, the dynamic stage and the static stage both are there. When both are present we call it domino logic. Now what happens is, in case of pre-charge, obviously since this MOSFET and this MOSFETs are being pre-charged, this capacitance will get charged and this capacitance over here will get charged. As a result, what will happen? W will be equal to 1 and Y will be equal to 1. And since this is static CMOS, if W is 1, X will become 0 because it's going to an inverter. If Y is 1, Z will become 0 because this is going to inverter. So in pre-charge stage, W and Y are 1, X and Z are 0. And next, when we move to the evaluate stage, we are supposing that both inputs A, B and C are switched on. That is, have the both input, all the three inputs have high value. If all the three inputs are high, then what happens? This capacitors get discharged in this direction. If it gets discharged, W becomes 0. As we can see, in the evaluate period, W has become 0. If W becomes 0, our X will become 1 because this is a static inverter. So the X becomes 1. We can see here. Again, if X becomes 1, C is 1. So this capacitor will get a chance to get discharged, and as a result Y will become 0. If Y becomes 0, we have a static inverter here, so Z becomes 1. As a result, we have actually cascaded two NAND gates using uh, we have actually cascaded two AND gates using the static inverter in the middle, and this is called domino logic gates. Now the actual logic circuit would be, first we have a NAND gate. With that we have connected an inverter, and after that another NAND gate, another inverter. So that can be modified into this circuit, that is two AND gates are cascaded one after another. Now the problem with domino logic is that domino logic can perform the function of AND OR but not NAND NOR. Why is that? Because after every stage there is an inverter involved, and that inverter converts the NAND or NOR into AND or OR. In order to solve that problem, we use dual rail domino. What dual rail domino does is, it takes inputs in true and complementary form. That is, for example, in case of two input NAND gates, it will take inputs as A, B, A bar, B bar. It will take 4 inputs, and it produces the outputs in true and complementary form. That is, it produces the output of Y bar and Y. So now let us look at an example of AND and NAND gate. If we want to create a NAND gate, what happens is, our pull down network is in series and the inputs are A and B, and we have a pre-charge involved, and the output will be connected to a static CMOS, and the output would thus be A, B. The output will not be AB whole bar uh, because our domino gates cannot create the NAND outputs, that is inverted outputs. So now we want an output which will be AB whole bar, that is we want NAND operation. We can do that by creating, and we have already learned this this formula that a into b whole bar is equal to a bar plus b bar, we can implement that. How can we implement that? We know in case of pull down network, if two logics are in or two inputs are in addition format, that is in OR format, then they are placed in parallel. So we are placing them in parallel. Here we have b bar, here we have a bar, and we require the precharge as it is. Okay, now both precharges are connected together, and from here, if we use an inverter, here we'll get y is equal to ab whole bar. So by using the true and complementary inputs, we are getting true and complementary outputs. We get both ab and a bar b bar. So this logic is called dual rail domino logic. Dual rail domino because both y and y bar, true and complementary formats, are available. Now let us look at another example of XOR and XNOR. We know XOR is equal to a bar b plus ab bar, and XNOR is ab plus a bar b bar. Now we can see in this case XNOR is a underscore I means a bar, a underscore h means a. That is, h is the true form and I is the complementary form. So here we can see the left side is XNOR and the right side is XOR. And here we have a and b and c, a bar and b bar in series. So these two will create a bar b bar. And again we have a and b in series. So this MOS and this MOSFET will create AB. So the output will become AB plus a bar b bar. Similarly, in case of XOR, we get this A inverse and B. These two will create a bar b, and again we have this A and B inverse in this direction. They will create a b bar. So we'll get output is equal to a bar b plus a b bar. It is to be noted that the example of AND gate we had shown was actually unfooted, and here we have an NMOS connected in series. So this is an example of footed dual logic domino gates. That is, we can make it both footed and unfooted as an when required. Now one problem is there that when the output is actually in the evaluation period, the output or since there is no Precharge involved, and if A is equal to 0, then what happens? The output is floating. If the output is floating, there is leakage, and as a result, the capacitor that was supposed to charge, make charge at this point, loses some current due to leakage and it gets discharged, and as a result, the output becomes smaller. This problem of leakage is solved. This problem of leakage is created by the floating output, and this problem of leakage is solved by using a weak keeper. What does this weak keeper do? The problem of leakage will happen if and only if at this point, at this node, the problem leakage will happen if and only if at this node the input is 1. That is, if that node the signal is 1. Why is that? Because precharge has already happened, that is, this capacitor has already charged, and since A is equal to 0, this capacitor has no place to get discharged. So at that stage the output is floating and the value of x is 1. If the value of x is 1, after the inverter the value of y becomes 0. If the value of y becomes 0, it switches on this transistor, and this transistor connects VDD to this point, and as a result the x becomes 1 and the capacitor keeps getting charged. So these type of transistors are called keepers, and these keepers ensure that whenever the output is floating, it ensures that the output maintains its fixed value. So the problem of leakage or floating output is solved by using keepers. Another problem is charge sharing. Why the charge sharing? We can see that we have two, in case of two input NAND gates, we have two inputs A and B, and as a result at this node we have a capacitor Cx and this node we have a capacitor Cy. So the output voltage will be shared by the two capacitors, and the total output voltage Vx or Vy would be Cy divided by Cx plus Cy into VDD. Now, as if the value of Cx is large, then what happens? The output voltage is not entirely VDD. The output voltage falls. So the capacitor actually shares the charges, and as a result, we can see since the charge is shared, the output voltage falls. Now, in order to solve the problem, what we can do, we can design the circuit in such a way that Cy is very large. But if Cy is very large, what happens? Since the capacitor is very large, and the delay component increases. So another way is including another precharge. That is, this precharge which was originally there was used to charge the capacitor Cy. We can add another precharge here which will charge the capacitor Cx. As a result, in the precharge stage, both the capacitor Cx and Cy will get charged, and there will be no shortage in charge in Cx in any form. As a result, charge will not get shared. Both will get individually charged, and this will ensure that the output is equal to VDD and output is does not fall from the definite value. Another problem is noise sensitivity. Noise sensitivity again is created from floating output. Since the output is floating, it is very much susceptible to noise. And the noise sources can be capacitance, crosstalk, charge sharing, as we have learned. Power supply can be noisy or feed through noise, and many more other noise sources can be there. And these noise sources actually may cause the logic to change. And our domino logic is really susceptible to noise. Again, when we are considering the power, in case of domino logic, we get or dynamic logic, whatever we use a clocked pull-up network. So since clock pull-up network, this clock is pre-charged for the half cycle, and the clock is evaluated for the half cycle. So the activity factor becomes very high. So domino logics have very high activity factors. Why is that? Because in every half cycle there is work, and more the frequency of the clock, the more the amount of work would increase. And as a result, and we can see that if the input is equal to 1, then output becomes 0. But in case of pre-charge, output will always be 1. So in pre-charge stage, the output will always be 1, and in the evaluate stage, the output may switch from 0 to 1 or 1 to 0. That is, if there is any change in the evaluate stage, there must be a change in the pre-charge stage. As a result, the activity factor or the activity quotient becomes very high. And if the output probability of 0.5, as in case of inverters, the activity factor is 0.5, and output rises and falls on half cycles. And the clock transistors even have activity factors of 1. And since the activity factor is very large, the power consumption sometimes becomes very large. As a result, our domino logic or dual rail domino logic or dynamic logic, whatever we may use, our power consumption is very high, and this is not very much power friendly. Domino logic still has some advantage. That is, first advantage, it is 1.3 to 2 times faster than CMOS logic. But the amount of disadvantage is very large. Firstly, complicated circuitry is required. Second, the problem of monotonicity, leakage, charge sharing, and noise are there. This domino logic has been widely used in microprocessors since 1990s, and now also these are used in some memories for ADA efficiency, but they have been largely displaced by static CMOS circuit. Our static CMOS circuit that we have learned in our earlier lecture is the most efficient circuit in terms of operation. That is, in all the trade-offs, if you consider all the trade-offs, our static CMOS circuit becomes most efficient. That's all for domino logic and dual rail domino logic. In the next lecture, we'll be learning about some other members of circuit families. Thank you.